Okay, this is lesson 4.3 on simple probability. For your warm-up, you're asked to reduce each of these fractions. And remember, to reduce a fraction, all you really have to do is find a number that divides into both of them, preferably if you can think of the biggest number that divides into both of them, because then you can just reduce it all at once in one single step. So if I'm looking at 20 over 65, clearly 5 divides into both of those. So 5 into 20 gives me 4. And then 5 into 65, that's tricky. Okay, 5 into 60, that's one I should know. That's 12. So 5 into 65 should be one more time, meaning 13. And because there's no other numbers that divide both into 4 and 13, my answer must be 4 divided by 13. And that's what you're being asked to do on all these first problems in the warm-up. In probability, there are two types of ways to consider predicting possible outcomes. The first is theoretical, meaning we just predict it based on what the numbers tell us. If we're rolling a die, then we know there's 6 total outcomes. We know that at any given roll, we'll get one of those. So the predicted probability for, say, getting a 2 would be 1 divided by 6. Whereas an experimental probability means we actually took the die, we rolled it 100 times, and then we found out how many times we got a 1, how many times we got a 2, how many times we got a 3, all the way up to how many times we got a 6. And then we calculate our probability based on what actually happened in that experiment. So any controlled or repeatable process is an experiment, and a single possible result of an experiment is what we call an outcome. If we made a list of all the outcomes that could happen, we'd call that the sample space. So if you look at this table down here, let's look at a couple of different experiments we could do. One is to flip a coin. The sample space is heads or tails. Those are the two things that possibly could happen. One possible event that could occur is flipping heads. And a possible outcome could be that that happens. I get a heads. So let's say we roll a die. Well, my sample space are the numbers 1 through 6. Those are the different things I could roll. An event would be rolling an even. An outcome would be I actually toss the die and I get a 2. That's an outcome. An event is a set of all the possible outcomes resulting from a particular event. So I shouldn't use the word event there, but let's say, again, rolling in evens. Well, then an event for that would be, the event rolling an even would include possibly getting a 2, possibly getting a 4, possibly getting a 6. So an event can include several outcomes. An event just defines the nature of the outcome. Think about pulling up to a traffic light. How many different outcomes are possible? So we're not talking about one that has like the blinking yellow or a green arrow. We're talking about a basic traffic light. You only have 3 choices there. And what are those 3 choices? Well, red, yellow, and green. So that's your sample space. So we're officially going to define probability as the likelihood that an event occurs. And we have an equation for this. The probability of any event happening is the number of ways it can happen divided by the total number of possible outcomes that could occur. Whenever we want to talk about the probability of something happening, we say P, capital P, and then in parentheses, we describe whatever that event is. So for example, the probability of event A happening is P of A. Let's apply this to an actual event. So let's say you rock up to a standard deck of cards. What's the probability that you reach up to the top, you take the top card off, and you find that it's an ace? Well, there's 4 total aces in the deck that you could pick, but there's 52 total cards that technically could be picked. So number of aces divided by total number of cards, and we reduce that to 1 over 13. Now, we could express our answer as a fraction, as we do here. We could also express it as a decimal, or we could express it as a percentage. In a second example, we say, well, what about the word banana? If we reached into a cup and had all the letters of the word banana in there, what's the probability we'd pick an N? Well, you'll notice in the word banana there's 2 N's, and there's a total of 7 letters in the word bananas. So 2 possible letters that are N divided by 7 total letters, and your probability is 2 over 7. And again, we could have shown that as a decimal or a percent. 4 basic important rules of probability. The probability of anything is going to fall somewhere between 0 and 1. You'll never get a negative probability. You'll never get a probability that exceeds 1. You can't get more than 100% chance that something will happen. So an impossible event would have a 0% probability, or 0, and a sure event would have a probability of 1, or 100%. The complement of a probability is like saying, what's the probability that something doesn't happen? So for example, if we go back up to 47, I said, what's the probability of drawing n? We said 2 out of 7. If I were to tell you what's the probability of not drawing an n, you would tell me 5 out of 7, because that's the probability of drawing any other piece that is not an n. We call that the complement. There's a different notation for the complement. Instead of saying p not a, we could also write p of a to this little c superscript. That's a symbol that means the complement of event A happening. Okay, remember that we could determine how many outcomes were possible using permutations and combinations. That's what we've been doing in the previous 2 lessons. So let's say that you're given 3 flavors, strawberry, orange, and banana, and you can mix 2. You want to find the probability that a randomly selected mixture includes orange. Now, you could just mentally kind of work your way through this, but we know that all the mixes with orange are 2 total mixes. All right, you can have orange and banana, orange and strawberry. That's the only 2 that will have orange in the mix. All possible flavors, where you're going to mix 2 of these, is going to be 3 things in combination taken 2 at a time. Combination, because we don't care what order those ingredients go into our mix. I mean, it could be orange, banana, banana, orange. It wouldn't matter. Okay, so all the mixes that included orange were 2. All the possible mixes, 3C2, which gives us 3. So in other words, our possibilities are 2 divided by 3, or 0.6 repeating, or 66.6% chance of that happening. Let's take a look at 53. You have a playlist of 6 songs, and you set the playlist to random, but this particular player doesn't repeat songs when it's on random. So what's the probability that the songs play in the same order that they're listed on the playlist? Song 1, 2, 3, 4, 5, 6. Well, you'll notice I put a 1 on top here because there's only one possible way that the songs could play in order from 1 to 6. All right? And then what are all the ways they could play? Well, I can take 6 songs and make tons of permutations with them. So 6 things taken 6 at a time, which is 720. Therefore, my probability is 1 over 720 chance that these songs could play in order from 1 to 6. All right, and there's 719 other possibilities they could play in a different order. Let's take a look at 54, which is the most complicated example here. You have 4 favorite songs on this same playlist. All right, back from problem 53. What's the probability that 2 of your favorite songs are played first in any order? Okay, so in any order means order doesn't matter. So the ways your 2 favorite songs could play is, well, you have 4 favorite songs, and you want to know how many ways 2 of them can play. So 4C2, there's 6, and then all the ways 2 songs could be played first, well, all 6 songs, and how many ways could 2 of them be the first 2 to go? Right, and it wouldn't matter which of those 2 played first and then second, but we want to know how many different ways 2 of your favorites could potentially be played first, and so we have to do 6C2. 6 over 15, I can reduce that to 2/5. I could also show that as 0.4 or 40%. Let's take a look at a few exercises. If I'm given this spinner and someone says how many outcomes are there in the spinner at left, well, I just count the number of ways the spinner could land. So there's, 8 spaces there. Therefore, I have 8 different ways the spinner could land. All right. So, taking a look at problem, let's say 62. What's the probability of getting a number on the spinner? Well, there are no spinners. That's the probability of an impossible event. Therefore, your probability here would be 0. All right, how about problem 63? If we spin the spinner 400 times, how many times would we expect it to land on a vowel? Let's go back to problem 58. How many vowels are there? Well, let's see. E, U, A, there's 3. I, 4, O, 5. So 5 of the 8 spots on the spinner are vowels. We have a 5 in 8 chance. So what I can do is I can say, okay, if 5/8 of the time I expect to get a vowel, I'll times that by 400, and that will give me the number of times I would expect it to land on a valve. That, of course, would be 250 different ways. Alright, this is a case of geometric probability. If a dart hits this target randomly, how many equally likely outcomes are there? Well, we can see that there's 36 by counting all the spaces. So if someone asks us, what is the probability of getting a bullseye, we would say, well, there's 4 squares in the bullseye. And there's a total of 36 total squares. So we can see that 4 bullseye squares divided by 36 total squares we could hit would reduce to a probability of 1/9, which again, you could express as a decimal or fraction, or as a percentage. And on problem 70, if it wants to know if we threw the dart 180 times, how many times would you expect it to hit in a corner? Well, there's 1, 2, 3, 4 corners. So 4 divided by 36 gives us, again, a probability of 1/9. Times 180 total throws, we'd expect 20 times to hit the corners. Probabilities can be represented in frequency diagrams and Venn diagrams, and I'm pretty sure you've had some experience with these at some point in your life. If we're looking at this table right here with strawberry, banana, vanilla, and chocolate, and someone asked me on 73, what is the probability of getting vanilla and strawberry in your yogurt? I'm going to say, well, the only place where I see vanilla and strawberry in one single yogurt is right here, 26, that box right there where those two columns and rows intersect. So 26 over 100 total possible outcomes. I could reduce that to 13 over 50. The decimal equivalent is 0.26. Moving down to the Venn diagram, if someone asks me what's the probability of A and B, well, the only things I see in this Venn diagram that are in both the A and B circles for events are these 5 things. There's a total of 50 things if I add everything up. So 5 that are A and B divided by 50 total things, and I could reduce that to 1/10. Back to 77, what's the probability of B? Well, everything that's in the circle B is B, so 20 plus 5 is 25, divided by a total of 50 different outcomes, that reduces to 1/2. 81, what's the probability of not A and not B? Well, if it's not A and not B, it can't be in the circle for A, can't be in the circle for B. All that's left are these 12 things right here. So 12 divided by 50, and that reduces to 6 out of 25. Alright, someone gives me this two-way diagram, this time with a few probabilities, and I'm supposed to fill out the whole diagram. Every box counts for a point. So they've given me these 3. I can kind of just use a process of elimination here to figure out the other ones now. If the probability of being a bird is 0.55, that means everything that's a bird, whether it's red or not, probability is 0.55. So 0.25 of them are red. Well, that means this one must just be the rest. So 0.3 would go here, where it says not red. I could just keep moving around the table from there and filling in all the things I don't know. Remember, all the possibilities have to add up to 100%. That's why this 1's in this corner. Okay, we're nearing the end. This time they give us some probabilities, and they ask us to place them in the appropriate place in the Venn diagram. I'll give you one of these. So if someone tells me probability of cats and stripes, meaning I'm a cat that has stripes, and that's 11 out of 100, that number 11 is going to go right here in the middle, because those are animals that are both cats and they still have stripes too. Alright? Now when you go to get stripes, remember, you've already put an 11 right here. So if the probability of having stripes is 57 out of 100 and you've already put 11 here, you can just put whatever's left after you have already accounted for 11. So 57 minus 11 will go in this box. Alright, well that's it for me. If you guys have any questions, always feel free to come see me. Happy to help.